This is what is, let me start from the beginning. Welcome to session 9. We will have one quiz now to start with. Now, let me explain this. This quiz talks about set of instructions which are in the pipeline, and this pipeline is having a forwarding logic built into it. But still, the question is whether there will be any stall for any instruction, and if so, how many cycles. As I explained earlier, stall means the instruction cannot proceed and it has to be waiting. It should be made to wait. So that will happen only when even the forwarding logic is not able to provide the input, or any resource is not available, or any operands are not available. Then that instruction will be forced to stay in the same stage. So if you look at this set of instruction, load is the first instruction, which is fetching some value into x1 a register, and then the x1 value, x1 is used in subsequent instructions. Now we need to see where will we get the value from the memory, which cycle, which time, at what time, and then whether forwarding logic will it be able to help in getting this value to the instructions. Now, if you look at the instruction stages, it is a memory read. It will be completed only at the end of this memory cycle. The memory will be read. If everything is working fine, data memory, there is no cache miss, the data is available, then it can be completed by end of memory stage. Whereas the subtract instruction needs the value in x1 during this cycle. Even if it is not available during this cycle, it at least needs it by the beginning of this cycle if forwarding logic can provide the data. If forwarding logic can give it, it can take it here and ALU can complete the subtract operation. But the problem is it is not available during this time frame from the pipeline register. Even if forwarding logic is there, it doesn't, data is not available. Remember one thing, forwarding only can give the data only if it is available, otherwise it cannot. So it is because it is available only here, it can't be fed backwards. So this instruction will be stalled. That means what will happen is this EX stage will be moved here. So this will become a EX stage, this will become a memory stage, and this will become a write back stage for this instruction. And once one instruction gets stalled in the pipeline, the remaining instructions also stalled. Okay, it's not that if one instruction is stalled, the remaining instruction can proceed further. All of them will be just stalled. They will be where they are. They cannot proceed further. So effectively, all these instructions also will get delayed by a cycle. Okay, so effectively one cycle of stall will happen. Okay, that's the answer. Okay, so this is a thing which you have studied in the forwarding logic, which I explained. This is called the data hazard, and we are trying to solve using forwarding. And forwarding cannot be a solution in all cases. There will be a situation like this where even with forwarding, the instructions cannot proceed and a stall cannot be prevented. So that's what I'm trying to make you understand using this particular quiz. Okay, so this picture shows stall. Okay, once one is stalled, all of them will be stalled and the remaining will continue. So if you see this instruction is stalled at IF, so it will start with ID. Here IF should have started here, but it is starting delayed, and EX should have been here, it is moved. So you can see that everything is moved by one cycle. So where there is a stall, the complete column will be stalled, all the instructions will be stalled, and whatever may be the state, it will continue after that. It's like freezing the pipeline. It will freeze the pipeline for a moment, for a one cycle, okay, or two cycles based on how long it takes. Let me explain when you can have more than one cycle of stall. In this case, it is possible. This is a memory read, I told, and I assume that the data is available at the end of this cycle, which is possible only if the data which is asked by this instruction is available in the data cache. If it is not, then it is a cache miss. Then it has to be either got from the lower cache memories or maybe from main memory. So this one cycle of stall can even extend to 2 or 3 cycles, provided there is if there is no data in the cache. This particular data is not available in the cache, which needs to be brought from some lower memory. Then the stall can be extended. That means this stall will continue maybe for some more time, and then the rest of the instructions will continue. This is how things work, okay, in a real life scenario, okay. Fine. Now, let me ask another question here. Without the support of forwarding, what would be the stall incurred by instruction I+1? If suppose forwarding is not there, assume that cache miss is not happening, but forwarding is not there. In that case, even at the end of this memory cycle, the data will not be available. So in fact, it has to be delayed by 2 more cycles, because it has to be read from the ID cycle, has to be replaced, okay, moved. So it will take another additional cycle if forwarding is not there, okay. Okay, fine. Let me continue further. Now, I am going to teach you something little more complex than what I have been telling so far. So far, we have seen data processing instructions. We didn't touch upon control flow instructions. So I explained it little bit before we ended the last class. So let me explain what all the branch instructions and what different types of branch instruction, and then we will go into pipeline impact of that instruction on the pipeline, okay. So control flow instructions are branch instructions where the flow of the program is changing. The flow of program can be, there are 2 ways of branches. One is unconditional branches and another is conditional branches. It is similar to calling a procedure. If suppose you are calling a process, function, you are in a high level language, you are executing some instruction and then calling a function, irrespective of any if condition. Then the program flow will be like this, and then it will jump to the calling procedure. That procedure or a function will be in some other memory. So instruction flow goes there and then executes all the instructions here, and then when it returns, it will continue from the instruction it left off. So when you have a function call in your higher level language, then it will be replaced with a equivalent assembly language called call or a branch. There are so many, based on the processor, it will be different assembly instruction. So it's an unconditional jump, irrespective of any condition. If the PC, the program counter, reaches this area place, it will be jumping to the new location. That means what? Already the pipeline would have fetched the instruction which are next to it, okay. Then it is deciding that it has to jump to some other location. In that case, it's a new set of instructions which are going to be executed. So the instruction which have been fetched need to be removed from the pipeline, and new set of instructions have to be brought, starting from the address where it is jumping. So one thing you have to remember, the so far data hazards only made the pipeline to stall and continue. It was not causing too much of a disturbance to the pipeline. But control flow instructions cause much more damage, in the sense much more performance impact, because it is not only stopping the instruction execution, it is also flushing the pipeline and starting afresh. It is like what we did now. We stopped the whole meeting and then we started off fresh in another meeting. So you have to flush whatever is there in the pipeline, because it is a jump to some other location. It is not, it is an unconditional jump or a call. Call is also equivalent to jumping to some other location. Only difference is, in a call, after executing some set of instruction, if it encounters a return statement, it will come back, okay. The flow will come back. So you might have remembered all that link register in ARM, which which stores the value, return address, and then comes back, okay. We are not going into the details of those. So difference between jump and a call is, call also is a long jump. It is going to some other location in the memory to execute some set of instruction. But when it encounters a return statement, it is supposed to come back to the next instruction after the call. That is the call routine. And jump routine, once it goes, it doesn't come back. It will keep on executing it. If there is another jump to this location, it may come back. Otherwise, it will continue. So there's the difference between a call and a jump, or a branch with no, call routine. But both are unconditional. That means it will happen with, even without 100% that transition is going to happen. That's called unconditional jump. Conditional jump means, if you remember in our high level language, we use if statement. We'll say that if there is x is equal to 1, then we say we want to execute here, otherwise else condition. So it will go in only if this condition is true. So similar to that, there are some instructions in the processor which will check the flag condition and then jump. So then there is a possibility that either the instruction will continue further, or it may go to some other location in the assembly, okay, in terms of assembly. So that is called conditional jump. So it may be loop closing branch condition, or it may be other conditional branches, switch statement or if conditions and all that. Unconditional jumps could be a simple jump, or a branch to subroutine, or return from subroutine. It's also a jump because it is coming back from one set of flow of instruction to another one. So return is also a conditional jump, and call routine is also a conditional jump, okay, conditional branch. Now let me explain. Branches are used to transfer the control unconditionally to another location in the program. Unconditional branches are always taken. It's called always taken. There is no optional choice. It has to be taken. Okay. There is nothing called being tested something true. Okay. It's a subroutine call equivalent to, one of the example is equivalent subroutine call. The control is taken to a particular location, and when return instruction is executed, it will come back. If it is a subroutine call, it is likely to come back when it encounters a return instruction. Okay. Now, this is achieved by either, this is something to talk about the particular processor implementation. The return address may be pushed into the stack, or it could be put in the link register in if it is ARM processor. Different processors handles this differently. Okay. Only thing is, some mechanism will be there to come back to the address which is next to the subroutine call. Now we are not bothered about those things, whether it is coming back using stack or it is coming back through link register. That is not the discussion here. We are talking about what is the impact of those control flow instructions causing on the pipeline, because we are still worrying about pipeline. So the control flow instructions is a huge problem in ILP, instruction level process parallelism. So since many instructions could be in different stages, now in a pipeline, different instructions have already come in, and then one jump happens. Now different instructions in the pipeline have to be removed from the pipeline, and new set of instructions have to be brought into the pipeline. So there is a loss of few cycles. It's not even one cycle or two cycle. It could be much more. Okay. So let me explain it with an example. An instruction called branch to a target address, branch target. Okay. Don't worry about whether this is an ARM instruction or a MIPS instruction. If there is one branch target. Okay. I'm showing an ARM instruction actually, but showing you the MIPS pipeline. It doesn't matter because you are familiar with this instruction. I'm showing it. Now, let me explain this. This is very important. Understand it. Then the rest of the discussion becomes easier. Okay. Let me go slow. See, when you see a assembly instruction, there are some labels. Okay. Labels means it is understood by the compiler or assembler or the tool linker is a name given to a address in the memory. Okay. A variable name is a label given to a location in the data memory, whereas the label in the program is a label given to a an instruction in the memory. Okay, so if you see here, target is an label, an address where the instruction X is. We are not bothered about what is this. Come here. Now our program counter is pointing at the B target instruction. Okay, so it is a branch instruction, and PC plus 4, we are assuming it is a MIPS with 32-bit processor with instruction width of 32 bits. So PC will be incremented by 4 and some other instruction Y is sitting there. Now what is expected of it? When a PC points here and B target is executed, it's a branch to target. That means the control should go back to target address. That means it should start picking up instruction X and start executing. It's an unconditional branch. There is no conditional check here. And instruction Y should not be executed. Instruction Y should not be executed because it is coming after that. But there will be an instruction, there will be a memory. Okay, assume there are something coming here, but since this instruction says control should go back, the processor should go back in the actual case condition. But what happens in the pipeline? Pipeline keep fetching the instructions one after the other. So by the time it picks up B target is picked up here, and then it is not even decoded. It doesn't even know it's a branch instruction. So it passes the IR value, the instruction register value, and then it allows this stage of the decode stage to understand what is this instruction about. The next instruction is fetched, which is instruction Y. Remember, the instruction Y has come into the pipeline, but it should not be executed. But you cannot prevent it from coming into the pipeline because you don't even know this is a branch instruction when it is fetched. So it will be fetched anyway, but later on, once the processor knows it's a branch instruction and it is supposed to go to the top address, it will ignore this instruction. It will ignore this instruction. It will not execute it further. It will flush the pipeline and then go back. Okay. So let me try to erase it. Okay. Now you might wonder, what are these values, what you see inside the instruction? Now that is very important. I showed you offset. This is whether it's a positive value or negative value. This offset is, I am showing it from this address, PC plus 4, some address, to the target where this instruction is. It is negative because always instructions are going in the increasing order addresses. So it's a negative value. And where is this stored? This offset, I will tell you. Now, how is the new location, the new address of the PC is computed? That is very important to understand. The new PC value is computed from the current PC value. Okay. Now, current PC value is not equal to PC, it is PC plus 4. Why? Because by the time this instruction has been understood or decoded that it is a branch instruction, PC has been incremented already. So it is PC plus 4 now. So now it has to find out this address. How will it find out? The CPU has to find out the new address somewhere here. Okay. From the instruction which is coming in, it will be able to find out provided the CPU has the information about the offset value from the current PC plus 4 value. Suppose the instruction B target has the information about how far the target label is from the PC plus 4 address, not PC address, not the address of this own instruction. It's the next instruction address. From there, how far is the label, whether in the towards the negative direction or towards the positive direction. What is the offset? It's a relative address. Why is the relative address given? Remember one thing, it's a 32-bit processor and the PC, the program counter, is also a 32-bit register, and we are trying to find out what is the new value of PC. If suppose instruction should hold the total value of the PC itself, it needs 32 bits of locations. But our instruction itself is 32-bit wide. It is not 64-bit. Either you have to increase the instruction bit or try to accommodate it within the 32-bit value. How can it be done? If you do a relative addressing in the jump, then it is possible, because you can use the existing PC value and add or subtract some value to that and try to get the target address. So you are trying to build or get a 32-bit address of the target instruction from a 16-bit value, which is an offset. So offset can be smaller because it is from the current location. You are saying plus or minus something. So I can limit my offset to some 16-bit value, which is a signed value, which I can extend it to. You can see that it can be extended to 32-bit. So no issue. Now, what is that I need to do? I have to use this ALU now, because I have to find the new address. The CPU has to find the new PC value, the target. Target is not there with the CPU. CPU only has this value offset, which is coming with the instruction. Okay, so let me explain now a little bit. This is the instruction format. This is the offset value, 16-bit value, which is coming along with the instruction. B is the opcode, branch opcode, whatever it is. So it has the offset. Now, who has found out this value? The offset value is computed by the assembler, because assembler knows what all the instructions are there in the memory, and from the location it will calculate from the PC plus 4. It will not calculate from PC. It will calculate from PC plus 4 because it knows about the pipeline. Okay, that's why I told you compiler or assembler should also have some knowledge of the processor. If there is a pipeline, it cannot find out, it cannot give the offset value from the PC. It has to give with respect to PC plus 4, because PC plus 4 only is used by the pipeline to compute the new address. So tool is aware of it. So it puts the offset value into the register, into the instruction, sorry. Along with the instruction, it comes. Now, you can write the equation now. Target in terms of offset. I am sure you will be able to write. Maybe I should have asked a question. Let you think about it. If I have to ask you to write an equation, okay, of what is the, I want you to write target address equal to something plus offset, sorry. I think it is very obvious now. You would have written it as PC plus 4 plus offset. You can write plus offset. Don't worry. Don't write minus here. It's a plus offset, because offset value itself is a signed value. It will have a negative value if it is to the top address. Okay, means it is a lower address. So you don't have to put a minus here. You put plus here. Target is equal to PC plus 4 plus offset is the equation. Okay, this is the equation. Now, who is computing it? CPU has to compute it, because it only has the offset value right now coming in, and the CPU is supposed to, when it is executing this instruction, means it is supposed to find the new PC value now, which is nothing but a target. It can be found out only when the CPU does this operation. It has to perform this operation. For doing this operation, it needs an ALU. Now, is there any ALU here? No. So it has to depend on this ALU. But so now it will compute it. Now let us now see the flow of this instruction. Okay, branch is coming in. As usual, what happens is the new value is computed already. No issues, because it has to fetch in the next cycle. It has to fetch the next instruction. So it will happen. Even if branch comes, it will happen. Okay. Now PC plus 4 is also, if you see, PC plus 4 is also available in the pipeline register. Always it is available, but based on the instruction being decoded, either this value will be taken or ignored. Remember, most of the things, actually data is flowing through the pipeline, but some may be taken, some may be ignored based on the instruction which is currently in the pipeline. Now, look at this. Now you should be able to find out what will happen in this stage. I think you should be able to now guess what I'm going to show. Okay, I'm sure most of you should be able to do. I already explained that it is supposed to do this. You know which are the path to take to perform this job. Okay, so as you guessed it correct, most of you might have guessed it, PC plus 4 will move to this pipeline register. Why it should come to this pipeline? Because it can be done only here. ALU is available only here. Okay, now you might wonder, when this instruction is decoded here, PC plus 4 is already fetched. Remember that. Keep in mind, it is going on fetching the next instruction. It is going to happen. Okay, nothing can be prevented. Now it cannot be prevented. Now, because you need to find out the new value to load the PC, that can be done only here. Because you have PC plus 4 here, you have the offset which has come along with the instruction. Now you know the equation to find out the new target address, which is nothing but using this adder. Now you know what should be selected in the mux. Now I am showing you only one path which I didn't show you so far, is this one which I am showing you now. It is going to happen now. Okay, so based on this branch instruction, these signals will be enabled, mux will be chosen. Accordingly, it will choose the particular input. So add operation will be chosen, target address is found. Now you have a target address which is there, which is to be the value to be loaded into PC. Now you will know what happened. Okay, you should know now what should happen now. This value should be loaded into PC, so that from the next cycle onwards, new PC is used for accessing the instruction. So far what has happened is, two instructions below this have been accessed already. PC plus 4 is accessed, that has come here now, because once this moves, naturally PC plus 4 will come here. When PC plus 4 is coming here, PC plus 8 is accessed here. Remember, you have to keep it in mind always, this is happening. Now I don't want to keep on fetching the wrong instruction, because what we are doing is we are making the CPU to do something which is not needed, because we know that these instructions are not required to be executed. It is happening because of the pipeline. The problem is because of the pipeline. Now we found the new value target. Okay, we have to somehow quickly load into PC. How will we do it? We have a already connection there. Okay, that's why the connections are already set. We have to enable it based on what instruction is being executed. Now most of you might have guessed it now. The target will move from here. Okay, you see that line already there, and then the control signal is generated, because it is a branch instruction. Control is generated. Okay, and it is controlling this mux to choose this value. Now it has to choose this value. It is loading the new value of PC into the new value of value into the PC. Okay, so you know that it is chosen, mux is chosen, it has chosen this is an input. Now PC should be loaded. So that I will show you in the next slide. Sorry. So this is always generated because it's an unconditional branch. So now next slide, I'm showing you that the new PC value now getting into the PC and then getting accessed also. So what will happen is instruction X will be accessed now, because we have computed the new target address and loaded into PC, so that that condition has happened. The branch has happened. Now what happens to those instruction PC plus 4 and PC plus 8 which was inside the pipeline? They are all ignored. You might wonder, if this instruction has come into this stage, will it cause any problem to the state of the CPU? Please remember, state of the CPU is nothing but the values of registers. The values of registers have not been modified. Maybe suppose there was a subtract instruction R1, R2, R3 here, which came here and started decoding and then started fetching the value. It has only read those values, register values, and it is not, maybe it would have even performed the operation, but by the time it came, we actually loaded the new value. But even if it performs, it has not returned back the value into the register. So the registers are safe. even though this instruction came into the pipeline, the state of the CPU has not been changed. So these are all the things which I want, if not all of you, some of you or many of you should be able to appreciate, because as per the program, we don't want this instruction to cause any disturbance to the program, so it will be taken care of. Okay, so I hope this is clear to you. This is very important thing to understand. So let me explain it a little bit, which I have already spoken about. Based on the label target, offset is computed by, from the PC+4, how much is the offset, and a new PC address is computed in the EX stage. Okay, it is embedded into the instruction. That value is embedded into the instruction, and new PC is loaded into the PC. So value is loaded into the PC at the beginning of memory cycle of branch instruction, and instruction X is accessed. Okay, that's what I explained to you with the simulation. How many cycles are wasted? 2 cycles are wasted here. Okay, we have accessed 2 instruction, PC+4 and PC+8, and we wasted 2 cycles, but we achieved again, going back to where we want to. So these are the instruction which was accessed. Okay, I hope this is clear. The pipeline is flushed, so this is flushed, and then it is reset, new, everything is emptied, and the new instruction is going to be coming into the pipeline. Okay, so this is the implementation of a branch with the pipeline of MIPS. I showed you unconditional branch. I will show you now conditional branch. Okay, okay, I hope you understood now so far what has happened. Now, what is the difference in unconditional branch and conditional branch? What is the difference between these two? I told you already. Conditional branch means it will check one flag. It could be carry flag or a zero flag or a combination of some flags based on the instruction. If you remember, BNE, branch not equal to, in ARM you might have heard it, and BEQ, branch equal to. Okay, that means what? These instructions, branch provided not equal to, some 2 values are compared, maybe using compare instruction, and if they are not equal, it will be branching, otherwise it will continue with the next instruction. That means what? If not equal to means zero flag is not set, equal to means zero flag is set. So some instruction above this BNE or BEQ, compare instruction will be there, or maybe some add or instruction, some instruction may be there which is disturbing the flag, zero flag, and based on the state of the zero flag, this instruction is taking a decision whether I should branch or not. Okay, so now pipeline, how it behaves when conditional branch comes. Okay, now I am going to show you only one control flow which I have not shown you at all. Only this one. Okay, I have not shown you only this, rest of it we have seen. Okay, with this I am sure you can understand this picture 100%. Okay, 100% you will understand why these these connections are there. I think everything is covered. Okay, now BEQ in ARM syntax, everything is same except BEQ. Everything is same, so I don't have to repeat anything in this instruction. So what is happening? This branch will happen, not always. It is a conditional branch provided a zero flag is set. So it is going to check the zero flag. Now I have to explain to you something little more in terms of implementation. If you remember the ARM processor architecture, we said that so there are so many registers, and then we also told there is a flags registers, okay, which is having zero flag, carry flag, overflow flag, so many flags. And then we in fact saw some instructions also accessing the flag register, assembly instruction accessing the flag register. So the flags is a register. Okay, only thing is some bits are having some flags and some bits are not used, maybe reserved for some future use, but those flags are also part of the instruction register set. Okay, so flags are actually maintained as part of the register set along with R1, R2, R3, PC, everything. It is flags also part of it. Now, what is this condition? BEQ is supposed to do if zero flag is equal to 1, make the PC is equal to target, change the PC value. If it is not, continue with the sequential execution. That means whatever you are doing, continue with whatever you do not branch. So this is what is supposed to happen. Now I am explaining to you the flags is some set of bits which are grouped together and put in a flags register, which is also maintained as a part of registers so that instructions can access it or use it. But the problem here is flags are impacted by the operation done by ALU. Okay, flags are affected by ALU operation. So it is maintained in this physically and affected by the hardware which is performing the ALU operation here. Remember one thing, in the pipeline, what is happening when this is being used, there is one instruction here, and when some operation is happening, there is another instruction there. There are two instructions parallelly doing something. So any impact of flag due to this instruction should be reflected on the flags register only when we declare this instruction is complete. When this instruction is completely executed, only then it should be reflected. Otherwise, we will have an incomplete value. So to do that, we can actually perform it easily. We can use the pipeline register to pass on the flag, and then when we write back the result, we can write back the flag also into it. Okay, it is not shown, it depends on the implementation of a processor. Most likely this will be the way it may be done. Okay, so keep it in mind. Even if you don't completely understand, I want you to go and think about it. Ask me doubts if you have anything. If you don't understand it fully what is happening, I am telling you physically it is maintained here, but actually contents are computed here, and it should be reflected on the flags when it is supposed to be done. When it is supposed to be done, only when this instruction which is here completes the execution. It will complete when it goes out on the write back stage. It has to be delayed by 2 cycles. If it has to be delayed, the flags value should be passed across the pipeline register and then put back into the flags. Okay, that will be taken care of. Okay, now don't worry about it. If you don't understand fully also, it's okay. It's only I'm showing you some additional information I'm giving you. Okay, now let us understand this fully. Easy. PC is incremented. This instruction is coming in. BEQ is coming into the pipeline. And what happens? As usual, it will come in. PC plus 4 is coming here. Offset is computed here. The same thing. It is all, nothing is different except one condition, that the branch might do the execution of changing the PC provided this zero flag is set. Okay, this will come here and then go back here only if this zero flag is set. Otherwise it will not go back. Okay, it will continue as if nothing has happened. Okay, so that's the normal way it is computed. So assume that branch is taken, so we will call it as a taken when actually this branch is, the zero flag is set and then it is going there. Branch is taken or not taken. There are two possibilities. If it is taken, the new value will be loaded and what you saw will be happening. In the unconditional case, what happens, it will happen. Otherwise, what will happen? It is not jumping. That means what? It is supposed to execute PC plus 4, PC plus 8, which is already in the pipeline anyway. So it will continue. So there is no flushing of pipeline happening. There is no changing of PC value happening. It will continue as if nothing happened. So if branch is not taken, the execution continues with the old values of instructions which have been fetched. Okay, these are the instructions which are fetched below this. Okay, I think I have explained it enough. So conditional branch explained. The processing area is same as unconditional branch. The difference is that during the EX stage, BEQ of BEQ, apart from computing the target address, flag is also checked. So you have to compute the, it can be done in a hardware. Okay, don't think that one is dependent on the other. Checking the flag can be another hardware which can do it. And it can also check selectively, either carry flag or a overflow flag or a combination of the flags. That can be done based on the instruction. Okay, so it will done in the EX stage. Based on the flag value, the branch is taken or not taken. So here also 2 cycles will be wasted, and this I explained it to you. Flags are getting affected by the ALU, whereas it is maintained in the register set. ALU is in the EX stage. So what happens is, when the particular instruction gets completed, if it is supposed to impact the flags, it will be written. If you remember, in ARM, there are some instructions which will affect the flag. Some may not affect the flag. So based on the condition, it will be selectively written into the flags register, or it may not be written. Okay. Those who remember the ARM can relate it what I am saying. That's all, guys. Okay, I have explained it now. What is done for conditional branch and unconditional branch? Let me summarize. Unconditional branch, what happens? We need to find the offset plus the current PC plus 4 value. We need to add these two, compute the new address, load into the PC, and then get it. Okay. So that is what is done in unconditional branch. In terms of in case of conditional branch, what happens is, condition is also checked. It could be a 0 flag or any other flag, and then based on the condition, either branch will be taken. What I mean by branch will be taken means PC will be loaded with a new value, or selectively it will not be loaded. So it will be computing it anyway. New address will be computed, but it won't be used. It won't be put into the PC, because remember, computing cannot be stopped because it is happening in the same stage where the flag is also checked. So hardware just goes through it and computes it. It is not wasting any cycle. Within the same cycle, computation also happens, and the flag checking is also happening. And if flag checking results that branch should not be taken, then the offset value or the new target value which is computed is ignored, and the instruction will continue, okay, as if nothing has happened. So this is what is happening in the pipeline. Now I will show you one optimization which we can do. Okay, I will stop with this. I wanted to cover more, but I don't think I can do. So I will stop with that. I want to do some optimization. What optimization? I don't want to waste 2 cycles now. See, if I depend on this ALU to perform the PC plus 4 plus offset, I am delaying the computation. Is it true? Let me check. See, what you need a offset value, and you need the PC plus 4 value, which was coming from here earlier. Actually, these two values are already available here. Okay, it is already available in this stage, but we unnecessarily delayed computing the new target address by 1 cycle because we didn't have an ALU here. We didn't have an adder here. We don't need a complete ALU. Remember one thing, ALU is a more complex circuitry which can perform multiplication, division, all that operations. Okay, ALU is much more than an adder. Adder is only, it can perform addition. Addition means it can be a signed addition, 2's complement addition. So it can perform addition or subtraction effectively, but it can't do multiplication or division, which is not needed. We are not trying to compute the multiplication of some address. We just want to add the offset. So we don't need a ALU here. We need only an adder. So it's a very small circuitry which can be put. Okay, ALU is not used now for offset computation. Okay, so what are we gaining? We are doing the computation ahead. If it is the case, it is easier now, because even decision, if you want to take, it is shown here. Okay, but it depends on the implementation. Maybe we can do it here also. It depends on the implementation of whether you are checking the flag here. But at least if it's an unconditional jump, you should be able to do it here. Okay, conditional jump has to come here, but unconditional jump can be done here. I will explain, if time permits, I'll explain you what is the reason why it is done there. But let me explain now. We are talking about unconditional jump. In unconditional jump, what we don't need a flag. Okay, for a moment, don't think about conditional jump. We need only the new address to be computed. Now, for new address of a PC, if you want to compute, we need a adder, which we added here. Now, PC plus 4 is available here, give it to this guy. Offset is available here, give it to this guy. add it, new value you find. Now it's an unconditional jump. There is no condition to check. So it will be immediately fed to the PC and a new PC will be found. Now, what is the gain you have in terms of stall? How many cycles it is going to waste now? Earlier, it wasted 2 cycles. It accessed PC plus 4 and PC plus 8. Then only the new address is fetched. Now, what happens is when this instruction branch equal to instruction comes in this case, it is new address is computed here. PC plus 4 is accessed here. Okay. PC plus 4 is just accessed from the memory and immediately new address is put into the PC. So one cycle of accessing PC plus 4 is wasted. So we are saving one cycle by adding one adder here. Okay. So new address is accessed by beginning of EX stage. So we are accessing the beginning of EX, not even beginning of memory. Here itself we are accessing the new address. So wasting only one cycle. I hope this is clear because this is very important for you to understand the next section that I plan to do. What we have covered, I will end with a quiz now. We have a branch instruction I. Instruction I plus 1 is used, and with the adder in ID stage. Remember, adder is in ID stage. This branch is an unconditional branch. Okay. If this is an unconditional branch. From the picture, you should be able to make out what I am trying to show you. Now, I want you to answer one question. There is no poll. It is always either it's unconditional branch with branch taken. Okay. Assume that it is an unconditional branch with a branch taken, of course. I want you to tell me what is the address accessed here and what is the address accessed here. You see here, this instruction is ignored. This instruction is ignored. That's why you are seeing nothing is shown here and next instructions are coming here. Okay, it is shown in this way. Okay. I'll give you just 1 minute to think about, not even 1 minute, I'll give you less than that. What is the address it is fetching? If suppose PC is the address this is fetching, this will be a PC plus 4. Now we are computing the new address in the ID stage itself. Okay, new address is found in the ID stage itself. That means the new target address is accessed during the next cycle. So this will access PC plus 4 and this will access target address, whatever is the branch it is going. It is shown already. There is nothing great about it. So PC plus 4 and target. Okay, and the same instruction set you will be able to understand it. The new target address is computed one cycle earlier now because all the needed values are available already. So we are doing it by adding a new adder circuit. That's all. We are wasting only one cycle because of branch, unconditional branch. Okay, I will stop here because you are all tired after the test.